Hi, everyone. Welcome to the presentation on unsupervised self-training for unsupervised cross-lingual transfer. The motivation of our work lies behind the scarcity of label data, and we know that it is especially so for code switched data and code switched applications. Label data is scarce and noisy, and hence there is a need to come up with unsupervised and semi-supervised methods which are able to handle code switching. Before we get into the unsupervised self-training framework, let's look at the data sets that we work with. So we work with English, Spanglish, Tanglish, and Malayalam English data sets for sentiment analysis. The thing to notice here is that all the four languages are code mixed with English, and there are differences in domains and data imbalances, and these differences are something that we deal with in our unsupervised framework. So the two data sets, English and Spanglish, they are Twitter data sets, and they are also relatively balanced, whereas the Tanglish and Malayalam English data sets are YouTube comments, and they're relatively imbalanced compared to English and Spanglish. So let's get to the unsupervised self-training framework. It is this framework is a minor twist to the self-training algorithm, which is a semi-supervised algorithm. So we start with a base model, which in our case will be trained on English sentiment data because all our code mixed languages are code switched with English. We start with a base model trained on English sentiment analysis, trained for English sentiment analysis, and make zero shot predictions. Then we select the n most confident zero shot predictions and use the predicted labels as ground truth to fine tune the base model. And then we make predictions on the remaining data set using the new model that we got after fine tuning. Then we again select the n most confident sentences, and then we again fine tune them using the predicted labels as ground truth. So we never use the actual labels. And we keep doing that until a certain stopping condition. So for zero shot predictions, we use a Roberta based model pre-trained on 60 million English tweets and fine tuned on a sentiment analysis data set for English tweets, which had 20,000, roughly 20,000 utterances. This is the same model as released in the paper Tweet Eval and is also available open source. And here we can see the zero shot results. One thing to note here is that our base model, the Roberta based Tweet Eval sentiment analysis model, it's a 3-class classifier, whereas in our study, we're only doing binary classification. So we're only dealing with positive and negative classes. This is why even in the case of binary classification, we're getting accuracies less than 50% because one of the labels predicted by the base model is a neutral label, which we count as incorrect prediction. Now, this framework, the model also learns to not make neutral predictions. So it's the base model is trained on as a 3-class classifier, but we can, as we fine tune it, it becomes a 2-class classifier. There are two selection strategies that we use, which are important to note here. Vanilla selection, which selects the top n sentences of each predicted class. So these selection strategies correspond to the selection blocks, which are highlighted here. And ratio selection, which selects the sentences from each class in ratio of which their distribution is in the data set. So this ratio selection strategy tries to compensate for the imbalance, or tries to overcome the challenges given by the imbalanced data sets, imbalanced class distribution of the underlying data set. So finally, we arrive at the model results. So what we have here are the results for the 4 datasets that we have. The zero shot results in this column provides the floor to our performance, the performance of our model. That zero shot results, the unsupervised self-training method should not produce results below a zero shot prediction. And the supervised results are where we use actual labels to train our model, and the supervised results give us a ceiling of how good we can do. And these 2 columns are unsupervised self-training, vanilla selection, and ratio selection. We can see that the English and Spanglish results for vanilla and ratio selection are roughly the same, and that's because the two data sets are balanced. So there is no real difference between vanilla and ratio selection. But for Tanglish and Malayalam English, we can see significant improvement with ratio selection, and that kind of incorporates and compensates for the underlying imbalanced data distribution. Overall, we see that the unsupervised self-training ratio results are very close to the supervised results. So Spanglish is as close as 1% to the supervised results, whereas English and Malayalam English are the furthest away, which are 7%. I'm comparing the F1 scores here between the USD ratio and supervised. So finally, we also provide an insight as to how the model is performing and try to understand if the model is learning the code switch language or not, starting off with only the model being trained only on English. To do this, we define a quantity called Hindi token ratio. So we assign a number Hindi token ratio to each sentence or each tweet or each utterance, which is equal to the number of Hindi tokens in in the sentence divided by the total number of words. So this is specifically right now done for English because it's taken as a use case, but it is generalizable to any of the data sets that we use. The distribution of the data set, the count represents the number of utterances, number of tweets, for example, that have a Hindi token ratio given on the x-axis. So we see that more more tweets have larger amounts of Hindi than they have English. And we can also see this in the class-wise distribution. We see that a large amount of negative sentiment tweets have more Hindi than English. So this graph depicts the learning dynamics of our algorithm. So the zero-shot performance shows the performance of the base model, which is just trained on English data. We see that it performs decently well when the Hindi token ratio is low, which means that the input sentences have larger amount of English. But as the amount of Hindi in the sentence increases, the performance decreases. Now, this is an expected behavior, but we want that when the model is trained under our unsupervised self-training framework, the model begins to perform well in this region as well. And this is kind of what we see as the model is trained under the unsupervised self-training. Even for high Hindi token ratios or for sentences that lie in this region, the performance increases. Next, we look at a video showing the learning dynamics of uh, the model under this framework and see how the performance improves in this region where the Hindi token ratio is high. So here we see that the model performance improves over time as in this region where the Hindi token ratio is high. Let's look at it again. And this is going on with every iteration of the unsupervised self-training framework. So to conclude, we proposed an unsupervised self-training framework, which is a minor twist to the self-training algorithm, which efficiently leverages cross-lingual transfer. And the algorithm, we tested it for 4 data sets, which have different language families, different domains, data set sizes, data set imbalances. And we also presented different training strategies to encounter those differences. And we also present an extensive analysis of the learning dynamics of the unsupervised algorithm. And right now, our framework works we've tested it for a binary classification problem. And in the future, we look to use this framework for more complicated problems, starting off with, say, multi-class classification. Thank you, everyone, for listening, and have a nice day.